Now, due to lack of time, we're going to limit our study of mixed strategy to games with exactly 2 players, each of which has 2 possible strategies. And although it's simplified, it's enough to grasp the flavor of the subject and the flavor of the reasoning in the subject. A mixed strategy for a player with 2 strategies, let's call them A and B, is going to be a choice of probabilities P1 and P2. Because they're probabilities, they're between 0 and 1, such that P1 plus P2 equals 1. So the player will select strategy A with probability P1 and strategy B with probability P2, which is 1 minus P1. And the player should make this choice in a random way so that their opponent cannot detect a pattern in their play, so the opponent doesn't know what's going to come next or does not know which strategy they're about to play. So this is in keeping with our assumptions that these are simultaneous move games. So, for example, the player might use a spinner to decide, or perhaps the hands on your watch, to decide which strategy to use for the next play. The row player's mixed strategy is going to be represented as what I would call a row matrix, with P1 is the first entry, P2 is the second, so P1 is the probability that they play strategy A, the first strategy, and P2, the probability that they play their second strategy in the order given. And the column player's mixed strategy is going to be represented in a column, and that would be Q1 and Q2, where Q1 is the probability that the column player plays their first strategy, and Q2 the probability that they play their second strategy. Recall our example from fencing, where both players had the option of either attacking, which we call A, or holding back at the beginning of each bout. And we set up a payoff matrix showing the expected number of points for Rhonda, the row player, and in each of the 4 possible scenarios. So suppose Rhonda plays the mixed strategy written as 0.5, 0.5. This means that Rhonda attacks off the line. She plays strategy A 50% of the time, and she holds back 50% of the time. And she does this in an unpredictable way, so her opponent cannot detect a pattern in her behavior and doesn't know which one she's going to do, whether she's going to attack or hold back at the beginning of the next bout. On the other hand, if Kathy played a strategy given by the column matrix, or the column 0.7, 0.3, this means that Kathy attacks off the line 70% of the time. She plays her first strategy 70% of the time, and she holds back 30% of the time, and her choice for the next bout can't be predicted by Rhonda. Note that a fixed strategy can be represented as a special case of a mixed strategy. So the mixed strategy 1-0 means that Rhonda always attacks off the line, and it means that she always plays strategy A. How do we decide between strategies? Well, we're going to use expected payoff to make this decision. So the strategy which gives a player the greater expected payoff is the one that they should choose. So for the row player R, the strategy which maximizes his or her expected payoff should be chosen. And for the column player C, the strategy which minimizes R's expected payoff in the long run through repeated play should be the preferred strategy. When both players have only 2 strategies, calculating the expected payoff for R when you know the strategies for both players is relatively easy. And of course, when you know the expected payoff for R, you also know the expected payoff for C. And when more strategies are involved, it's best to use matrix multiplication to do these calculations. We're going to stick to 2 strategies. So let's see how we might calculate the expected payoff for 2 given mixed strategies for row player R, column player C, playing a zero-sum simultaneous move game. And it's implicitly assumed that the players make their choice of strategy independently of each other in this scenario. That's always an implicit assumption for our zero-sum simultaneous move games. So let's suppose the matrix looks like this, and we're going to use general letters to denote the payoffs, A, B, C, and D. And we assume that R has 2 strategies. We'll call them R1 and R2, and C has 2 strategies, C1 and C2. And let's also assume that R plays a mixed strategy given by P1 and P2, and C plays a mixed strategy given by Q1 and Q2. Because of this assumption that it's a simultaneous move game and they choose their strategies independently, the probability that R will choose R1 and C will choose C2 is the product of the probabilities that R will choose R1 and C will choose C2. So it's going to be P1 times Q1. And this comes from our old formula for independent events. The probability of A intersection B is the probability of A times the probability of B. And this is exactly the formula which allows us to calculate the expected payoff for R in this situation. So the payoff for R is going to vary from game to game. So it's always going to be exactly A, B, C, or D, and it's a random variable. So every time these 2 players play, one of these payoffs is going to happen. And the probability that this payoff will happen is going to be the probability that the scenario underlying that payoff happens. So we let X denote the payoff for R. And this is a random variable, and this is the payoff on each play of the game. We want to calculate the expected value of this random variable X. So if this game is played repeatedly, one of 4 things can happen for the payoff for R. It might either be A, B, C, or D on any particular play of this game. And what the payoff is depends on the choices made by both players. So if R chooses R1 and C chooses C1, the payoff for R is going to be A. And the probability that that's going to happen is the product of the probabilities P1, the probability that R plays R1 and C plays C1. So it's going to be P1 times Q1. And the probability that the payoff is C is going to be the probability that R plays R2 and C plays C1. So that's going to be P2 times Q1, etc., etc. Now to calculate the expected value of this random variable X, we need to multiply the payoffs, the value of X, by their probability. So multiplying the entry in the second column times its probability, we get the entry in the last column. First one is A times the probability that A happens, which is P1 times Q1, etc., etc. The last one is the payoff, which is D, payoff for R, times its probability, which is P2 times Q2. And then we add those to get the expected value of X. Now the reason I'm doing this in an abstract way is because I'm going to use this formula later. And so we see if we gather together the terms with Q1 in it and pull out the Q1, we get that the coefficient of Q1 is A times P1 plus C times P2. And if we gather together the terms with Q2 in it, we get that the coefficient of Q2 is B times P1 plus D times P2. And these will be important numbers in deciding in the very best strategy later. Here's an example. So consider this example, Rhonda and Kathy, who are playing, who are fencing, and they both have strategy of attacking or holding back, and we have the payoff matrix for Rhonda as given here. And let's suppose that Rhonda plays the strategy, the 50-50 strategy. She chooses to attack 50% of the time and to hold back 50% of the time, but she does so in a random manner so that Kathy can't anticipate what she does. And Kathy chooses to attack 70% of the time and hold back 30% of the time, but again she does that in a random manner so that Rhonda can't tell what she's going to do next. What's the expected payoff for Rhonda here in the long run through repeated play of this game? And what's the long run expected payoff for Kathy given these two particular strategies? Well, let's go through our calculation with the numbers. So we have 4 possible scenarios with 4 possible payoffs. Here A is 0.5, B is minus 0.2, C is minus 0.3, and D is 0.5. And the choices underlying those payoffs made by both players are what determine the probability. So the probability that the payoff for Rhonda will be 0.5, which is her expected payoff for that particular strategy, the expected number of points she gains. So the probability that that will happen is the probability that Rhonda will attack and Kathy will attack simultaneously. And we see we can find these probabilities in the strategies of both players. So we multiply the probabilities to get the probability that both of those things will happen because of independence. So the probability is 0.5 times 0.7, which is 0.35, and then in our last column we multiply each possible outcome times its probability, so multiplying the payoff 0.5 times its probability gives us 0.175. And likewise, for each of the 4 possible scenarios, we calculate the probability for the given payoff, and then multiplying the payoff times its probability, we get an entry in our last column of the table. And then adding the possible payoffs times their probabilities gives us the long run expected payoff for Rhonda when both players play these mixed strategies. So the expected long run payoff for Rhonda is 0.115. It's positive, and this means that with both of these strategies, the expected long run payoff for Kathy is minus that, because this is a zero-sum game. So Kathy, with this strategy, given that Rhonda continues playing the 50-50 strategy, her long run expected payoff, or she can expect to lose an average of 0.115 points per play in the long run if both persist with these strategies. And Rhonda can expect to gain those 0.115 points per game in the long run if both persist with these strategies. So again, this expected value is just meaningful through repeated play with the given strategies.